So this is sulfur dioxide gas, and this is nitrogen dioxide gas. Remember, the double arrows indicate that this is a reversible reaction, and it produces sulfur trioxide gas and nitrogen monoxide gas. These are all gases that are components of pollution. So you're going to sometimes see these called rice charts or ice charts. The R just stands for the balanced chemical reaction. I tend to use ice charts. I don't know. I guess I just like it better. So my problem states, a 1 liter flask was filled with 2 moles of gaseous SO2 and 2 moles of gaseous NO2 and heated. After equilibrium was reached, it was found that 1.30 moles of gaseous nitrogen monoxide was present. Assuming this reaction occurs under these conditions, calculate the value of the equilibrium constant K for this reaction. So let's write in there. Remember, I told you that you have to make sure you have molarity. This happens to be in a 1 liter container. So if we have 2.00 moles in a 1 liter container, it's simply 2.00 molar for each of these. If it doesn't mention that we put sulfur trioxide or nitrogen monoxide in, we're going to assume it's 0. So obviously you cannot have less than 0. So the negative sign in this case is going to go onto the reactants. So this might be different for each set of circumstances. You have to kind of analyze it. The one thing you know for sure is that you cannot have a negative concentration. So if any of the concentrations are 0, they definitely have to have a plus sign, and anybody else who's on the same side of the reactants products yield sign has to have the same sign. There's no coefficients here, so it's going to be minus x plus x plus x, like such. And then in the problem, it also told us that at equilibrium, after equilibrium was reached, it was found that 1.3 moles of gaseous NO was present. .30 molar. So just like we did BCA charts, remember BCA charts were with moles. Now we're doing ice charts that's with molarity or any units of pressure. Pressure can also be used. Kc is for equilibrium constant that refers to concentration, and Kp is equilibrium concentration that refers to pressure. Kc and Kp are the same only when you have the same number of moles of gas on each side of the reaction. So here's my equation right here that tells me what the value of x is. 0 plus x equals 1.30. So I know that x is equal to 1.30. So now I can plug that in for all of my x's. Like such. These become 2.0 minus 1.30 for both of them. So let's get our K expression. If you remember, our K expression is products over reactants. So it's going to be SO3 brackets to indicate concentration, which is what we're dealing with here. You would see a P for pressure if you were using pressure units. Let's plug in our values. Each of these is 1.30. and each of these is 0.70. So when I type in my calculator 1.30 squared divided by 0.70 squared, I get an answer of 3.45. Now with K value like that, does that favor the products or the reactants? That favors the products. Anything over 1. I want to add a couple side notes there too. If you see a K value that I'm just making up K values, that is like, let's say 3.2 times 10 to the minus 9, that is a super, super, super small number. And remember, it's products over reactants. So this would be the same as saying 1, 2, 3, 4, 5, 6, 7, 8. That means that there's very little products formed. So you might see this referred to as the reaction doesn't noticeably happen because most of the reactants will stay as reactants and very little bit will turn into products. You can also see a K value like this. So that's the same as, this is a reaction that will be referred to saying that it goes basically to completion. That means that most of the reactants will end up as products and very little of the reactants will stay as reactants. So those are the things that you're going to see K referred to as. Either the reaction doesn't really happen, or the reaction pretty much goes to completion. Or if you have a number like this, you're just going to say, oh, that definitely happens, but it favors the products. So our next problem is going to be a little bit different in that we don't just have reactants when we start this chemical reaction. We also have products. So the problem reads, at a particular temperature, K equals 3.75. So they gave us the K value. For this reaction. If all 4 gases had an initial concentration of 0.80, calculate the equilibrium concentration of the gases. So now we have to do a little bit of analysis to figure out which side gets the negative and which side gets the positive. If one reactant gets a negative, they all get a negative. If one reactant gets a positive, they all get a positive. So the negatives and positives are split up by the yield sign, and they remain consistent between reactants and products. So now I have to look at my K value. Remember, this K value, we already decided that favors the products. So we know when all is said and done, we're going to have more products than we have reactants. Right now, we have equal amount of products and reactants. So the products are going to get the plus sign, and the reactants are going to get the negative sign here. That's not always the case. So this is what you have to do if you're in a situation where you have both products and reactants to start with. You have to look to the K value to decide which one gets the plus and which one gets the minus. Again, no coefficients. So it's all just X. Okay, remind ourselves K is concentration of SO3 times the concentration of NO over the concentration of SO2 times the concentration of NO2. Now let's plug in. I'm going to leave out some zeros. It doesn't change my significant figures. I'm just leaving it out so I can see what's going on better. So if you're a math person, you might look at this and be like, oh, I'm going to FOIL that out and everything's going to be good, right? And then I'm going to do this long, complicated problem. But if you're not a math person, you're going to say, I don't want to do that. So let's look at a pattern here for those of you who are looking for a shortcut, which would be me, like such. I can recognize that pattern, and now my problem becomes a little bit easier because I don't necessarily have to FOIL. What I can do is take the square root of each side. When I take the square root of each side, my problem becomes much easier. It's 0.8 plus x over 0.8 minus x equals the square root of 3.75 or 1.936. So I'm going to do some straightforward algebra here, which I'm sure everybody's pretty good at this kind of stuff by now. So I'll multiply each side by this, and I end up with 0.8 plus x equals 1.549 minus 1.936 minus x. Now I have to be careful. I'm going to show you the mistake that most people make because I want to deal with positives, obviously, right? So I'm going to add 1.396x to each side. I'm going to add 1.936x to each side. And a lot of times people forget I already have 1x here. So this becomes 2.936x. A lot of people forget that and they just put down that 1.936x. Now I'm going to subtract 0.8 from each side. And I can solve for x by dividing each side by 2.936. And I get a value of 0.2552. That's the value for x. So if you go up here, we can put that in here instead of x. And I can calculate my actual concentrations at equilibrium. This would be 1.0552, 1.0552, and this would be 0.5448. I actually have 3 sig figs, so I would round this to 0.545 and this to 1.055 molar. So the concentrations of SO2 and NO are 1.055 molar, and the concentrations of SO2 and NO2 are 0.545 molar. So there's just a couple examples of 2 types of ice charts that you might be running into. One where you have to calculate K from the ice chart, or one where you're given K and you have to calculate the concentrations of reactants and products.